okay, we'll just go to demonstration, then try to have a look at, okay, what all thing that I've shown, how do we able to demonstrate these all those variations over here. So let me just again share my screen. Let me go to okay, LabsLand. Okay, this is, I hope my screen is visible now. Okay, this is what we have in LabsLand. Okay, I just entered with my credentials, and this is my laboratory. Of course, this is a C amplifier, and this is how it looks. And then we have a for each and every experiment. You can see we have introductory video for every experiment, and we have a video. Now these introductory videos are very short duration, maybe hardly 5 minutes. It will give the bird view of, okay, how the things are happening. So what all variation that can be done, what I explained there right before, so we could able to see the same thing in this short video. And then this particular video showcases, okay, upon changing what parameter what will affect. And then we have a exhaustive manual for the C amplifier, and we have lots of assignment question for the students, so that after going through this particular lab, so students have to actually submit the assignment, so then only you will be graded. So let me straight away go to the common emitter amplifier laboratory, which is housed in LabsLand server. So it's now redirecting. Now, okay, this is what is common emitter amplifier. And then you can see, of course, every student will get 20 minutes time to conduct the experiment. The beauty of this particular environment is platform is we're going to have the schematic, and you can see there is a circuit view showcasing how does the circuit is connected, and you can see there is a ammeter which is showing the collector current of this particular amplifier for this selected values of R and C. And you can see there is a oscilloscope giving the two important waveforms of input voltage and output voltage. It has got the key parameters like, okay, input voltage, output voltage peak to peak. It is also giving the mean voltage of the output voltage. It is also showcasing what is the frequency of the signal. And more importantly, you can see this is a Bode plot, the frequency response of that amplifier for that particular parameters that has been chosen. You can see this is a complete response, and there are 3 cursors placed appropriately so that you can do the measurement. So what we'll do is we'll just slightly go deeper and then try to find out, okay, what is the impact of changing some RC. Suppose if I change RC, we know that as long as the MOSFET, the BJT remains in active region, so the collector current won't change. So let me just change this from 2.2k to 1 kilo ohm. You can see, I think you might have noticed, let me just go back to 2.2k. Please notice here, okay, there is a 2.2k resistor and this LED is on. So this is an LED which is on, indicating that, okay, which all component of this particular circuit are in use. You can see I'm using this capacitor of there is a slight mistake here, this has been 0.1, and I'm using a R2 of 5.6k. You can see it is 5.6k, and correspondingly so and so. Suppose if I change this to 1 kilo ohm, you can see this will glow now. So meaning that, okay, now 1 kilo ohm is in action. You can see there is no change in the current. So this is the same thing what I'll get when I conduct the experiment in my lab also. But more importantly, what I'll do is I'll just slightly minimize this and show you that, okay, what is the impact of this on the output amplitude. Suppose if I change the resistance from, okay, 1k to 2.2k, can you notice that, okay, the amplitude has increased. So now it is 1.72. Suppose if I make this equal to 1k, this will become now I can say, of course, let me just, now it has become 1 point. Let me just make this 1k. You can see now it has become 1.2 volts. So from 1.72 it has reduced to 1.2, because naturally when you reduce the value of RC, the output amplitude will reduce. So that's what is reflecting here. You can see the mean voltage will also change as you change the value of RC. Of course, more importantly, let us just spend some time on this frequency response. Let me just make this slightly bigger in size so that we can able to make out the readings. You can see it is 3.68 megahertz is the bandwidth, and of course you can see this cutoff frequency is around 60. Sorry, this is the one which is at mid band. It is 62 kilohertz, and the one which is there over here, it is at 691 hertz. Okay, what I'll do is just have a look at this gain here. It is 31 dB and the bandwidth is 3.6 megahertz. I will change this to 2.2k. So when I change this to 2.2k, the gain should increase. You can see the gain has increased from 31 dB to 37 dB. The bandwidth has reduced from 3.6 to 1.9 megahertz. So this is what a student can able to visualize. Now what we did is we changed the value of RC, that is reflecting both in the time response as well in the frequency response. Now student can able to take the readings, take a screenshot of this, and then take it as a part of his report for submission. So similarly, suppose if I change the value of RC, sorry, R2, that the biasing resistor, I can see if I change it to 4.7k, as my VB reduces, you can see okay, effectively the base voltage, sorry, IB reduces. When IB reduces, naturally my IC will also reduce. You can see there is a very small change, but there is a huge variation in the value of current from almost 1000 microampere to hardly 477 microampere. Suppose if I change the value of CC from 0.01 to, sorry, 0.1 to 0.01, there is no change, but you can see there is a reflect of that over here. Okay, what I can do is we'll see the impact of this capacitance on the frequency response. Just have a look at this. You can see this is your lower cutoff frequency. It's at 3.7 kilohertz. What I'll do is I'll make this 0.1. It was 3.7 kilohertz. Now you can see it has become almost 534 hertz. 534 hertz. This way, student can able to certainly visualize the impact of each and every component on its response, so that he has got a lot of learning that could happen over here. Again, let me also demonstrate the change in the value of RE. When I say RE, it is not this entire resistance, the bypassing of this. Now everything is bypassed. Suppose if I bypass only 50 ohm, now this is 50 ohm. Now since the bypassing, it is not fully bypassed, so I have reduction in the amplitude that is reflecting here also, but this bandwidth almost remains constant. So of course, as I just showed in the tabular column, student can able to take the readings of this mid-band frequency, lower cutoff frequency, higher cutoff frequency. You can see the gains at different points. You can see these two are kept at 3 dB down. You can see it is minus 3.9. Let me just, okay, it's almost minus 3.0, and this is minus 2.99. So this is how student can able to visualize each and every experiment. So when he is conducting this particular type of experiment. So this is, of course, I'm just giving a very glimpse of this. So what we suggest is students should know the theory part of it, and it would be better for him to just know the theory before he start conducting. So otherwise it will be difficult for him to just, okay, he will simply take some readings, he'll not appreciate what is happening over there. So we'll just again go back to so maybe I'll just take a few questions, maybe in the chat box. I'll just see if you have anything, so that I can, yeah, maybe if any of you, any of the participants want any specific thing to be shown, you can please chat, okay, write in this chat box. I can just, because if I unmute, okay, let me just try unmute you people, and then let me just stop sharing so that I can. Okay, now I can unmute. Why don't all the participants mute yourself? Okay, one of the question what I have is, can we build the circuit in the change value option? Okay, unfortunately, at present situation, we are not giving the option for the user to have his own values, but certainly with the available values what we have, which is almost around 16 different combinations of R and C's, student can be comfortably doing the experiment for learning this particular concepts. Uh, of course, we don't have that option of rigging up his own circuit. So, is there any possibility of connecting the component built from scratch? Okay, as I said, this is mainly meant for, okay, once he understands this particular concept, if he wants to check it, so that's what the purpose is. Of course, we don't have him to build it from scratch, so he has to, of course, we want to just, okay, when we actually started this particular process, we had this in mind that, okay, how do we, when we are actually doing these concepts in the classroom, so how do we make students to make sure that, okay, he can able to understand the concept there in the classroom itself. So in order to make sure that, okay, he can understand the concept in the classroom itself, and then maybe immediately after the class he can just go back and start doing the experiment, so by himself, by conducting the experiment. So that's what is this. Of course, there's a question like, okay, can we use different transistors? Yes, we have option of changing transistor. Let me just showcase that. Uh, and can we use network theorems verification and further? Okay, network theorems and all those things, of course, it's not a part of the present laboratories, so we don't have that, but we can certainly just, okay, include such type of experiments also. So what I'll do is I'll just go back to uh, this, and then let me showcase, okay, what is the impact of this transistor. When I say transistor, it is Q1. We got the 3 transistor option, so this is Q1, and of course they're all similar make, SL100 1 2 3. So if I change it to SL100 SL102, now you can see there is a small change. So for 1 it was 471 microampere, for 2 it is, okay, 525 microampere. This is my collector current. For 3 it is, for 3 it's almost the same. You can see it is, they are very close to each other. So this way student can able to visualize, okay, all the transistors may not have same okay, internal structure or the parasitics and all those things. So that is one thing. Okay, let me just again go back to the chat and try to find out. Yeah, one question is, okay, full wave and half wave rectifiers. Okay, this full wave and half wave rectifiers, I'll demonstrate this in the real time laboratory in the afternoon session. We don't have this experiment in ultra concurrent lab. We'll certainly showcase this full wave and half wave rectifiers in the afternoon class. When we are changing, just a minute. Okay, there is a question. When are you changing specifications of each type? Can we take okay, of course we cannot take a real audio signal and give it to the circuit. No, we don't have that option of because all these are pre-recorded videos, so I don't have the option of what amplifying the signal that is there real time, that is, and then how both the transient frequency response measurements are done simultaneously. And of course, as I said, uh, we know that, okay, this whatever time response is there, I'm just putting is for 20 kilohertz signal, that is, you can see frequency is fixed. When I'm showing this, when I'm showing this, I'm actually sweeping the frequency from 100 hertz to 20 kilohertz. They are done at different time, but they are with the values that have been specified here. So let me clarify that you can't do simultaneously, but I'm doing this, okay, Bode plot with the same parameters what have been mentioned in the circuit schematic. So that's a good question. Okay, you can't do it simultaneously. So, but I can record it and then show simultaneously. That's what is. Okay, then how both? Okay, no, this is, as I said, okay, they're not executed simultaneously. Okay, is it an open source? Sorry. Okay, this is not an open source. Of course, maybe immediately after this, okay, I'll just invite, okay, my industry partner, Dr. Pablo, to introduce himself, and then talk about the LMS, what he has to showcase you people. I'll just go back to the UNO presentation. I'll just okay, there is one more question. Okay, usual question from students is that, okay, why should we take 3 dB down bandwidth? Okay, find out the cutoff frequency. Is there any answer by the demonstration? Because we know that, okay, why 3 dB down means, okay, because there the power will be half, and then so that's why I'll always go for anything lesser than half power will not be sufficient for processing. So that's why we can say that it's midband to midband and the 3 dB frequency. Midband is the frequency where the gain is almost constant. So from either of the three the other two 3 dB frequencies. So let me just go back to my presentation. Now I'll just call upon Pablo to just okay Dr. Pablo is the CEO of LabsLand Spain. He actually stays in US. Now it's almost 1 a.m. at US. I'll just request Pablo to take over. Pablo, please.
Hi, can you hear me?
Yeah.
Perfect. Thank you. So I'm going to share my screen so as to be able to show the like the demo of the part of the FPGA and other types of laboratories we have, as well as the LMS. So I'm going to share this screen. Can you see my slides?
Not yet coming. Yeah, yes. It's coming.
Okay, perfect. Thank you very much. So as you have mentioned, we have two types of laboratories. One type is the ultra concurrent laboratories, which are the laboratories that are based on existing pre-recorded experiences like videos and data and all this. And we also have the real-time laboratories. Most of our laboratories are ultra concurrent. We have more laboratories on physics, chemistry, biology, covering the using the ultra concurrent approach. But we also have the other type, which is the ultra concurrent, the real-time laboratories. In that case, for example, this is a Arduino robot, like where the student writes code for Arduino, they write C code, and then they send it to one of the available robots, and we have different robots in South Africa, in Colombia, in Spain, and we're going to have soon also in Costa Rica. So in different countries, we have these robots, and the students will automatically go to one of these robots, and they will see how the robot moves in a real environment in real time. In the same way, we also have other types of Arduino laboratories based on Arduino Uno, so that the way to use it is the same. Like the student writes code and they submit it to a real Arduino device, and then they can manipulate with a set of switches and buttons and so on, and they can see how the real hardware works. We also have other laboratories of electronics, also in different locations in the US, in Germany, in Costa Rica, and in Spain. And also we have the FPGA laboratories. The FPGA laboratory is one type of laboratory based on FPGA devices. We support both Intel and Xilinx. We right now have more devices of Intel than of Xilinx, but we're deploying more copies of the Xilinx laboratories in Colombia and Spain. And in this case, what the student does, and this one I'm going to make a demonstration. If I go to the laboratories and I see the list of laboratories of LabsLand, there is one which is the FPA laboratory and the D1 and D2. If I go to the D1, for example, I will be able to write code in VHDL or in Verilog. We are going to support soon also System Verilog. And in the case of the VHDL, I will be able to write code here, and I can write here any message like Siddaganga Institute of Technology. So here, I'm basically...
Pablo, we are unable to see that particular thing, whatever you're typing. We are unable to see.
Oh, sorry, you're not... I'm not sharing my screen?
Yeah. Only that, example this.
Sorry, let me try to share my entire screen to see if that helps.
Because when you change your browser, that you may have to reshare
it. Okay, I'm going to... sorry.
Select that particular window which you want to show.
Yes, I'm going to share the whole screen just to make sure that I don't have problems with this. So can you see the VHDL?
Let us just wait.
Yes.
Yeah, that's fine.
Okay. So here what I have is the VHDL code that I can write, and I have different examples of code that I can use. But basically here I can write whatever I want. I can synthesize this code online. I don't have to connect to, I don't have to have any software. I don't have to have Quartus or Vivado in my computer. Whenever I synthesize, you might notice that it took very short time, because even if the code typically takes like 2 minutes to synthesize, given that somebody else, probably me, have already compiled this code, we have a cache system so that so as to make it the a better user experience for the student, and then I can upload it to the FPGA. So whenever I click here, I'm going to go to any of the available FPGA devices in different locations, and then I go to in real time. I'm connecting to Spain in this case, to the Public University of Navarra, and here I see the FPGA. And with that particular code, I think that if I turn on the switches, I will see the different LEDs turning on. If I press on the buttons, I will see that it says 1 or it says 2, or if I click on the button 3, it will say 3. Now, this is happening in real time. So this is really happening right now in Spain in one of the FPGA boards. The thing is, like, we have many different copies of these boards in different locations. Like in particular, the D1, we have it in Spain. We in 2 different locations. We're going to have it also in the University of Washington. Or University of Washington in the US. Also in the University of Michigan in the US, we're going to have the D2. In Colombia, we're going to have also the Xilinx boards, the Basis 3, and so on. So when the students access, they actually access any of the available boards, and they can access for a limited amount of time, for 2 minutes. They can come back to the code, they can change the code, and they can send it. Right now, the only inputs and outputs is the camera and the switches and buttons. But for October, we will also support VGA, like for the screen, also video input, and also audio. And also, you can do everything that you can do in the FPGA. Like the FPGA has a SD-RAM, and it has other components, so you can use those.
Pablo, it can be a bit slower. Yeah, slow down.
I'm sorry. So basically, in the FPA, you will be able to do more things than what you can do right now. But already right now, it's very useful for teaching VHDL and Verilog. The other thing I wanted to present is the environment of LabsLand. So what we have is one space per each institution. So Narasimhamurthy will show later, but there is like an option for creating here like different groups. Like you can see the webinar August 2020, but we can create other groups of like Arduino and the particular group of each institution. So each university has its own space, and in that space they can see the statistics of who has used the laboratory and when they have used the laboratory, and they can integrate it in different learning management systems. So it's not that we only support like our own system, that we of course do, but we also support that the students can access through Moodle, Canvas, Blackboard, Sakai, and other learning management systems. So each institution can choose how to use it. So, for example, this is the case of the Siddaganga Institute of Technology, where you are going to be able to access this particular group for you, so you can evaluate the tool and so on. You can also create a complete space for your institution, and right now it's free of charge until the month of September included. So you can have your own space and use it with the students until September. After that, it will have some pricing. And I just wanted to show other examples. Also, for example, this is also in India, and I can see the statistics on how people has used it in the previous course, like before June. And I can see that, for example, in this case, they used 66 students 2,000 times the laboratories, mainly, for example, in their case, the FPGA laboratories. So as Narasimhamurthy was saying, and this, like, I can see each day when they were using, at what time of the day, and all these things. As Narasimhamurthy was saying, this is like a local and global project, in the sense that universities in any part of the world are accessing also laboratories which are located in different countries. I showed the examples of South Africa and Colombia and Spain and the United States, and also other people from all over the world are accessing laboratories which are in India, such as the Siddaganga Institute of Technology laboratories. So in this case, like we have different institutions who have used these laboratories. Also, for example, in Malaysia, like I here, for example, I usually use this example because I have used extensively the tool. So if I check the previous course, I will be able to see that they used 17,000 times the laboratories, and they used it at every time of the day. This is local time in Malaysia. So except for Tuesdays at 6 o'clock in the morning, at any time of the day, they have all over the week they have people using the laboratories, and we can see like who was the student, when they used it, and all these things. So finally, as I mentioned, we have two types of laboratories, the ultra-concurrent ones and the real-time ones. Regarding pricing, in the case of India, the access to all the laboratories, the cost is like 600 rupees per student per year, and that's for accessing all the laboratories. But for example, if you only want to use the standard, like the ultra-concurrent laboratories, like those of physics and electronics, including the ones of the Siddaganga Institute of Technology, then the price is half that price. And here you can see like the different price for different what laboratories are included. And then you can also build your own custom plan where you say, I want to use the common collective amplifier, but also what about the electronics or things like that. So, and here you can see the different price of the different laboratories. So for now, what we are going to do is, as I said, like if you go to the main website, you have like a information that because of the COVID situation, we have provided free access since March until September, included in September, so anyone can register here. But if you don't want to register the institution, but you want just to test it first, we have created this space that has some link that the host will share, which is this link. That anybody with this link will be able to register and be part of this group and access the laboratories, and you will be able to test it and so on for a couple of weeks. And if you want to like proceed, then you can talk to us, or you can create the space through the platform. You can of course talk to Narasimhamurthy, so that he can also act as a proxy and so on. So this is all what I wanted to present, and I'm ready for any question or comment.
Yeah, that's perfect. Okay, just to add on, okay, because as Pablo mentioned, so they have tie-up with universities across the globe. So this is a very good platform so that we can able to showcase the things. So as you can see, he has got laboratories, okay, in physics, okay, where even in biology here they have got a lot of labs. And of course, I just welcome, suggest, any of you want to have develop any lab with LabsLand, so they're open for the collaboration. So because it's all for the student community, so we want to just make sure that they get best out of this particular whatever platform that we are creating. So thank you so much, Pablo, for giving a brief, wonderful presentation on the capabilities of LabsLand, and then of course even on the pricing. So as we can see that pricing is not an issue at all. So suppose if you want to have a bulk subscription for the entire institute, you can still go down to Pablo and then try to find out best pricing for the entire institute. So that can be certainly done at any point of time. So we will just again go back to the presentation what we are just proceeding. So let me just share my screen again, and then so let me just this is after Pablo's let me just this is what these are the few C amplifier assignments what we can think of giving to students. Now upon conducting these experiment, these number of variations, we can ask student to demonstrate that bandwidth bandwidth reduces as the voltage gain increases. So this is he has to identify out of those many combination of variations. So by doing what, the bandwidth reduces, but the gain increases. So he has to think a lot before he just answer this. Now these are all okay. Okay, the understanding, testing their understanding level. And we have to the second question, we show that the dominant pole is not altered by changing the bypassing amount of emitter degeneration. So so that he can able to understand what is this dominant pole, okay, why it is not affected by this, okay, emitter degeneration bypassing. So all those stuff he can able to understand, and he has to pick that right combination of readings so that he can able to answer that particular question. And then show that coupling capacitor and the input impedances decides the lower cutoff frequency. So if you change the value of CC, that is coupling capacitor, or the input impedance, the cutoff frequency, lower cutoff frequency of the amplifier will going to change. And again, show that in active region the collector current remains constant for the given base current. So this is these are all very pretty simple questions, but student have to pick a right combination of that readings out of these 16 combinations. He has to 16 into 3, that is 48 combinations, and he has to showcase this particular set of experiment. And then okay, we can ask him to just find out what is the phase margin of the system. So we have a CE amplifier, so he should be able to find out what is phase margin for this particular system. And of course, he can able to comment on the stability of the system. So how does the is the system stable? Okay, what is the margin available? And he can actually find out what is the phase of the output signal at midband and cutoff frequencies. So this is about okay, trying to read out the parameters from the frequency response. And then we can ask him to estimate what is the base to collector junction capacitance of the BJT by taking by knowing the different possible readings. So he can able to connect back to theory, and then he can certainly estimate the base to collector junction capacitance. And then this is what, okay, if two such C amplifiers are cascaded, what should be the input amplitude so that output is undistorted? Now these are all questions, because we can still end up with creating a number of questions from this, okay, C amplifier experiment. These are all a few assignment questions which we can think of giving to students, so that they can able to conduct the experiment more carefully, because they have to answer these questions. Yeah, maybe we'll just move on to the next, because we have a lot of experiments now. We'll just stick to 2 to 3 experiments and try to find out, okay, how does what are the capabilities of this low pass filter, okay, what I can do with this low pass filter. So the learning objective is, okay, I should be able to link it to the transfer function of this low pass filter. You can see, can I make the pole position movement? Of course, it has got 45 different parametric variations, and then it can do time response. We can visualize time response. We can see the amplitude, phase, and of course we can do the frequency response, passband gain, the cutoff frequency, and the roll off of the filter. These are the very important specifications of the low pass filter, which need to be observed whenever we perform the experiment. So we have ensured that, okay, all those things are considered while developing this particular video. Of course, you can see these are the equations what we are talking in terms of low pass filter. So we have this transfer function, there's a magnitude equation, there's a phase equation, and then we have this, okay, these are the typical ideal gain and the frequencies, phase. So it's a 0 dB and it is 0 degree, and magnitude is -3 dB and 45 degree phase shift. Of course, for low pass it is -45, and of course roll off is -20 dB per decade. So we can certainly see the demonstration of this particular low pass filter, and then we try to analyze. Okay, let me again start sharing. Okay, I'll go here. So I'll go to access my lab. Okay, I'll go to SIT. So in this, this is my low pass filter. This is the low pass filter. Okay, now, of course, even for this low pass filter, we have an introductory video. Of course, we'll be putting that parametric variation video also, and of course, the assignment will also be coming for this particular As we mentioned for the C amplifier, here also we have uh, the low pass filter whose schematic will be displayed here, and we can see there are 5 different frequencies that can be varied so that you can able to see the frequency response for different time response for different frequencies. I can change the value of resistance among these three: 1k, 10 kilo ohm, and then 1k in parallel with 10k. And then we have 3 different combinations of capacitors, and for each and everything we can able to find out what is the frequency response and the time response. So let me just see, keeping this at 100 hertz. Suppose if I make this bit less, what happens? Now you can see that there is a change in the value of C. Since it is 100 hertz, it's a low pass filter. Since the cutoff frequency is 1.59 kilohertz, since the input frequency is 10k, hardly there is no change. You can see hardly there is no change. Even though if I change from 0.01 to zero point 0.1, so we can ask a question to student, okay, why it is happening so? Because with 0.01 the cutoff frequency is 15 kilohertz, for 0.1 it is 1.5. Since the frequency is 100 hertz, because in both the cases it remains in pass band, so that's why there is no change here. Suppose if I redo the same thing with 4 kilohertz, you can see with this, okay, 0.01, since the cutoff frequency is 15 kilohertz, this 4 kilohertz comes in the pass band of this low pass filter. Now that's why you can see output is not too much reduced. Suppose if I make this zero point 0.1 microfarad, the cutoff frequency has now changed to 1.5 kilohertz. Since this is 4 kilohertz falls in the stop band of it, now we can see the of course output amplitude has reduced. So there is a reduction in the output amplitude because the cutoff frequency is changed. So these are some of the okay findings the student can able to notice here, because there's a flicker here because of some slight timing mistake. And you can see this is the frequency response. Let me just expand this and then showcase how where exactly we have placed the cursors. You can see we have placed 4 cursors. One is the pass band. You can see this is in pass band, which is at 222 hertz. You can see the frequency is almost 0 degree. Of course, it is -7 degree. If I just keep it slightly at a lower frequency, this phase will further reduce. And you can see the ideal cutoff frequency for this value of RC is 1.59 kilohertz. But what I'm getting practically is the cutoff frequency is 1.79 kilohertz at a 3 dB down here. You can see this is 3 dB down. And then you can see the roll off. This is the roll off. So I have kept it in the transition band. See the transition roll off is around minus 18.91 dB per decade. So we know that theoretically we are supposed to get 20 dB per decade, but we are getting very close to it as minus 18.91 dB per decade. So this way, by selecting a particular combination of values of R and C, student can able to visualize the time response for the given frequency and the frequency response for the sweep of the frequency. Please note here the sweep of the frequency is from 100 hertz to 100 kilohertz. This is what the sweep that we have done, which is being recorded at a different time. So when this is swept from 100 hertz to 100 kilohertz, so this is what is the response of that. Sorry, this is the one what we got. Okay, when the frequency is exactly 4 kilohertz, the input and the output waveform. Student can certainly able to note each and every reading and then comment on every reading that he has taken. Suppose if I make this again, let us make this equal to 0.01. Hardly there is no much variation that will happen here. It was 1.79 kilohertz. You can see it's almost close to that. What we have is, since it is 0.1 and 0.2, okay, this is just only 0.11 is get added. So there's no hardly no change in the frequency response of this. And of course here also it's almost comes very close to it. Now you can see 1.79, it's almost there. Of course you can see this is we actually changed the amplitudes here, so for to have that real-time effect of the signals. And of course this is how this has got 45 different combinations. We have got 5 different frequencies. We got 3 different values of 3 different values of R, 3 different values of C, which will make it 45 different combination. And of course this will actually indicate, you can see these two are on because both the capacitors are selected. What I'll do is I'll just select only one. You can see only one LED is on. So this is how we can able to take out the things. I'll just have a look at the chat box and then try to find out if I have any questions. Okay. So I have a question, is there a provision for user to change the oscilloscope setting? Like, okay, unfortunately we don't have the option of changing the settings for the values of R and C. But in the afternoon lab, when we actually give the access to a remote laboratory where a student will get complete control of the entire parameters. So as it is mentioned that okay, he will certainly have the option of changing the values of okay, time per division, volt per division, everything can be done in that remote laboratory. But since it is what ultra concurrent one and it is pre-recorded one, we don't have the option now here for this, especially for this particular lab. So that's what. Okay, but in afternoon lab, we'll certainly showcase that okay, student has got complete control of changing any amplitude, any frequency, any parameters, even these positions you can able to modify. Because I was telling that okay, if I just move this slightly towards lower frequencies, this will be much more lesser. That I can't do it here because this is pre-recorded one. But still again, this is still student can still make sure that okay, this is at a lower frequency, this phase shift is lesser, and you can see at exactly cutoff frequency we got a phase shift of almost minus 45 degree, which is theoretically very true. And as the frequency increases, the phase almost becomes minus 90 degree. So that's what the theory says. So those things a student can certainly able to visualize over here. Of course, we say the real-time laboratory, the hands-on is the best one. The second one is remote, okay, where you can have some okay access to some components. And this ultra concurrent, I'll rate it as the second best because, of course, even though you have a lot of constraints, but still we can able to learn many things. Without this, we would have not seen okay, what is the bandwidth and what is the phase and all those things. So all those things are the challenges and the constraints of this particular laboratory. So let me just take to amplifier experiment where I was showing you that there are 216 different variations. So let me just showcase that also, what all things that we have in that particular. So let me just again go back to this. Okay, I have this okay inverting amplifier. Let me access this inverting amplifier. This has actually got 216 different combinations. Now we have carefully chosen the combination such a way that okay, it can give the it can certainly give student a complete holistic view of okay, how does the circuit may perform at different parameters. Here you can see I can change the amplitude from different okay 0.1, 0.5 and 1 volt. And why we actually make this as 1 volt is even students should feel that okay, when the input amplitude is too much, okay, how does the output look like. Suppose if I say this is 1 volt and if I make the gain of around 10, suppose if I perform the experiment, so he should see something like this. So he should feel that okay, this is, suppose if he verifies the gain of this particular amplifier, even though I'm expecting a gain of minus 10, but he is getting hardly minus 3 or something. So you can see minus 3.5, minus 3.6. So he should be carefully enough. He should be carefully choosing the amplitude. Suppose if I make it 0.1, so that is pretty good. Now we can see the gain is almost equal to minus 10 because that minus is just okay encapsulated in that phase difference, that is out of phase thing. So these are some of the variation that we have incorporated in each and every experiment to just to give that okay real time situation what the students usually do in their labs. Because suppose if I keep it 1 volt and then start verifying what is the gain of this amplifier, so I can't say that okay, this my circuit is not working. So my circuit is perfect. The only thing is that okay, I didn't apply my proper signal. So of course, here what we have is we have one more amplifier, sorry, one more op amp, which is the usual mu A741. The other one, high frequency op amp, also we are considered to showcase that okay, how does that open loop gain of that amplifier, sorry, the op amp will matters a lot in the closed loop gain of the closed loop bandwidth of the system. So you can see now, suppose if I just do it for a gain of 10, so let me redo it for mu A741. So this is gain of 1. Okay, one thing I should say here, even though I made the amplitude as 1 here, that is reflecting only in the time response. But in the frequency response, the input amplitude is kept as 0.1 so that you have a proper gain that is coming out. Okay, let me just enlarge this and then find out what is the bandwidth of this amplifier. You can see bandwidth is around 51 kilohertz for mu A741. For mu A741, for a gain of 10, it is 51 kilohertz. So I will choose this mu A741 has got a relatively lesser open loop bandwidth, sorry, open loop gain. So let me have a OP37 has got pretty good open loop gain of the amplifier. If I make it equal to now we can see it has gone up from 55 kilohertz to 1.75 megahertz. It's almost okay 4 times or 3.5 times it has increased. So this is what is there is a this we want to showcase that okay the open loop gain of that op amp certainly matters for the closed loop bandwidth of the system and so on. So and of course there is no much variation in the closed loop gain because we are looking at a gain of hardly 10 here. Suppose if we go for larger gains, then only we can make out the difference. So of course that is still seen over here, that saturation, because I have a supply voltage of plus and minus volt, so it is clipping on either side. So we certainly have the 216 different combinations are coming because of we don't want to show only that lower frequencies, we want to also show that higher frequency sorry, high gain configuration. Now I can see there's a high gain of almost 100k. So sorry, this is a gain of 100, that is minus 100. Of course we have applied a voltage so low that okay, output is not distorted one. Please observe that okay, for mu A741 with a gain of 100, what is the bandwidth? So bandwidth is hardly 2.8 kilohertz. This is very bad in terms of with a gain of 100, the bandwidth is hardly 2.8 kilohertz. Suppose if I change this to OP37, the same bandwidth, you can see 3 dB bandwidth has gone almost close to 192 kilohertz. So there is a huge change in the bandwidth of this particular amplifier. So I got a question here. Is there any provision for student to change the oscilloscope setting? Again, as I mentioned, it is not there in this ultra concurrent, but we'll demonstrate the same in our remote lab in the afternoon session. So let me just okay showcase that okay. Of course, student can able to make out that okay, what the phase difference here. You can see the phase is almost minus 180 degree. You can see it is almost 178 degree in the pass band. They can see the difference is almost okay. You have almost minus 27 degree because of slight variations. Okay, it's not exactly at minus 40 minus 45 degree. And then of course because of these combination of standard and the when I say standard, the gain is of course gain also be 0.1 also. So what I'll do is I'll make this 10k. I'll make this 10k. The gain is now 0.1. You can see the bandwidth is so huge. So we have a very huge bandwidth over here. So you can see the gain is negative now. So it's a huge bandwidth. And of course it is going beyond this. So I could not, because my sweep is only up to 100. Okay, if I'm not, I think it's up to 10 megahertz only. I can't just go beyond that. So that's why I'm unable to see that 3 dB down. So these are the capabilities and the extremeness what you can look in this operational amplifier. So let me showcase one more experiment. What we have is the triple fire timer. I'll just go to that and then. So again, interesting one. Okay, what is that we have in triple fire timer? So this is my triple fire timer. I will access this. So as it is mentioned, we hardly have only 7 experiments, but of course there are a lot of experiments that are there in pipeline with the LabsLand. Now this is the Astable multivibrator experiment what we have using triple fire timer. Here we are providing one diode to either bypass this. Of course we named it as RCH, RDCH, or you can just name it as R1, R2. We have the option of changing that reference voltage. We have the option of changing the values of this RCH, RDCH, so that you can able to find out the impact of the resistors and okay, voltage source, and of course the diode. Because for this particular set of experiment, we just retained the value of timing capacitor as hardly 0.1 microfarad. So here we have three waveforms being displayed simultaneously. One is the output waveform, the capacitor charging, discharging, and the reference voltage. And you can see there are n number of parameter that can be seen here. So we got the period, that is the, which will give the frequency of the system, frequency of the square wave that you are already getting, and what is the positive width, and what is the duty cycle of the positive cycle, and then you can see what is the amplitude, the maximum amplitude. You can get what is the mean and all those things. Suppose if I change this control voltage from 3 volt to 4 volt, naturally the voltage at which this will go into charge, this will be slightly increased. So my frequency has reduced from 1.3 kilohertz to 1.1 kilohertz. You can see now this is that will reflect in your amplitude also. I can see this bandwidth has increased, but this off time remains constant. So all these details will be there given in the introductory videos and parametric variations, where students can able to rigorously look into each and every variation, then try to find out, okay, what is the impact of each and every component. And of course he can certainly connect all these to the theoretical equations what he has learned in the classroom, so that he can understand, okay, now this is just a beginning for a student to know, okay, how does the circuit works. Maybe once he gets to know, okay, how does the circuit works, then he can start building his own circuit using a combination of basic circuit that he has learned during this entire process of ultra concurrent lab. So assume that we have CE amplifier, CC amplifier. Upon doing CE and CC amplifier, he can just cascade both of them in the real-time laboratory, and he can do a okay, amplifier for audio amplification. You can put a speaker on the other side. Okay, someone was asking, can I able to amplify my mic signal? Yes, that can be certainly done. Okay, once you learn the basics of CE, CC, cascade them, apply the inputs through a mic, put it to a speaker. So those are the stuff a student can able to do it. Okay, what I'll do is I'll just go to 1 second. There was some issue with that sharing. Okay, somebody says I'm not getting, sir. Okay, let me just okay, any chance to give credentials? Okay, we'll certainly maybe after okay, the afternoon session, so I'll give you the credentials to log into this LabsLand, so that you can able to venture into different experiments that are there in LabsLand, and then you can certainly do it. Of course, it will be free till September, as Pablo said. So you can explore the things. So that's it. You can able to do with LabsLand. So let me just go to one more experiment. What we have is, what is the problem? There is no problem. Can you? No, nothing. No problem. Okay, let me just